infinity. Oops, I've got this level here. Good enough. Okay, so we are doing 7.8. Not yet. I'm going to talk about improper integrals. The kinds you can't invite to dinner parties. Okay, so what's an improper integral? It's not an integral with bad etiquette, it's this. So we say integral from a to b, so it's a classification of definite integrals of f of x dx is an improper integral. If you're sort of looking for one of two things to happen. Either one, your a equals minus infinity, or your b equals and or. B equals positive infinity, right? So if you have any infinite limits, which these sort of things come up in practice all the time, believe it or not, where you let the limit goes off to the limit on the integral go off to infinity, or two, f of x is undefined. At some point, probably several points on the interval. Let me emphasize that it's closed. On the closed interval, a, b. So it can either be undefined at a, undefined at b, or undefined at some point in between a and b. Probably several such points, but in either case, this is what we call an improper integral. So it's kind of an integral where the interval on which we're integrating does not behave very nicely, either because it goes off to infinity, which isn't really a number, so we have to figure out how to deal with that, or on some number on the interval that we are considering, the function misbehaves, like it's not undefined or something like that. Yeah?
Would it be the same thing if like a was positive and b was negative infinity?
No, because
oh, sorry. I was thinking up and down, not left and right. My bad.
Yeah. Okay, so yeah, it's left to right. So you can't have positive infinity on the left. There's no beyond infinity kind of thing here. So yeah, so this makes an improper integral. And integration, of course, as you know by now, it's computationally speaking, it's a lot more complicated than taking derivatives. With derivatives, you had those stupid rules, the product rule, quotient rule, the chain rule, and like you know when to apply them at any given time. But the integrals is a little bit trickier, but paradoxically, integrals are really forgiving. Like for a function to be differentiable, it has to be continuous, it has to be nicely behaved. Integrals actually don't care that much. Right? You can still integrate on an interval where the function is discontinuous or there are gaps or there are holes. An integral actually doesn't care that much. But we sort of have to be careful about division by zero and things like that anyway. So it turns out that we can evaluate such integrals. And if such an integral exists, we say that it converges if this guy is improper. But we can compute it anyway. Say this guy dx equals I. Then the integral is said to converge to I. So you can say this is an improper integral, meaning the function doesn't behave on the interval that we're talking about, or the interval goes on, is infinitely long, but I can still compute some meaningful value, meaning in terms of the area under the curve, I can still come up with a value that is meaningful in that sense. And if I can possibly come up with such a value, we say that the integral converges to that value. And it uses the word converge because it's very suggestive of how we will compute these values. So how do we compute improper integrals? The main strategy. So let's assuming we have some bad point that our function does not behave on, right? So I can't plug in a into my function because it's undefined for some reason. What's the next best thing? If I can't be at the point A, what's the next best thing? What would you think of? Right, so we're on this, our function is doing this thing, here's the value A. Now at A, catastrophe strikes. Right, so I can't actually talk about being at A. What's the next best thing that I can start to talk about?
The limit as it approaches.
The limit as I approach A. If I can't actually be at A, how about I get as close to A as humanly possible, or not humanly possible, because we're really dissecting these in an infinite number of values here. But we can use limits to approach the point. And that's sort of where this language of converge comes from, because the main strategy is to use limits to approach the bad points. No points are bad, but so that's sort of how we can get around this idea. If there's some point on our interval that's misbehaving, our function does not make sense there, then all we do is we kind of approach there. And why this kind of works is because if you think of what an integral is, it's measuring the area under a curve. Now, if at some point in the middle of this thing, there's a line, there's a value at which the function itself misbehaves, there's like a gap. Like how much does that take away from the area? Literally nothing. A line has no width, right? So if there's like one point that's misbehaving on this interval, the integral doesn't care. In fact, I can have a bunch of points missing on this interval, any finite number of points. In fact, a countably infinite number of points this can work for, but that's a different class. There can be all sort of these bad points that I can't touch on the function, but the area under the curve is not going to change by me removing those points. So all I do is try to fill in everything up until the limit of those points, and I can use a limit to do this. Because that's kind of why the integral is so forgiving. If we go back to the basics of what this is supposed to be computing, it's the area under the curve. But if you remove a single point from the curve, it doesn't change the area under the curve. Yeah?
So, if you're removing a point, like from, let's say, in the middle of the function, like in the exact middle of A, B, on the interval, do you even have to, could you just say, like, we're not going to worry about the limit at that point? We can just, because it doesn't actually affect it, and so you could just analyze it if this were a regular interval?
No, because you actually don't know how bad the point is.
Okay.
There are cases where it would affect the area. Not on a case like I just put here.
If it's an asymptote.
But there are cases if it's like an asymptote, or especially if we're going off to infinity, you never know. And there are some times where division by zero is so catastrophic that you can't change it even if it happens at a single point. So yeah, there are some times you can't actually work it out. And so to justify the fact that we can just ignore the point is what it means to get this value I.
Right.
I can say we can get a value for this precisely in the case that I can just ignore the fact that it messed up at that point. But that's not always true. There are times when being improper actually destroys the integral. There's no way to compute the area in any meaningful sense. Right? So I'm just showing you in the cases where things go okay and we can work around it, that's what happens. But there are times when things don't go okay. But in order to figure that out, we actually use limits to approach the point and see how the function behaves as we're approaching the point. Do things go crazy, or does it kind of settle at a nice value that we're happy with? Another thing that you want to, one sort of caveat to make sure the theory works out about how Riemann sums kind of work out as a theory, is you can only have one bad point. You can only deal with one point at a time. You really have to focus your efforts a little bit. You can only have one bad point per integral. But again, an integral overall is very forgiving with that, because we have this rule that says we can split up an interval as we please. Because we know that the integral from a to b of f of x dx is equal to, I can go from a to c of f of x dx plus the integral from c to b of f of x dx. So I can split intervals up. So if it has several bad points, I just break it up into pieces such that there's only one bad point on an interval. So for example, suppose I have an integral that goes from 0 to infinity of f of x dx, and f of x is undefined when x equals 1. Okay. So it turns out what I can do with that guy I can actually, first of all, I want to expose this bad point. So the fact that it's not going to work at 1 means I want 1 out in the open so I can deal with it and take a limit. Right, so I can start by that. But then, if you look at this integral here, there are 2 bad points to contend with, right? 1 is a bad point and infinity is a bad point, right? Because our functions don't behave at infinity, and we know this particular function doesn't behave at 1 also, but you can continue to break it up further. I can say go from 1 to 2, pick an arbitrary number, and then go from 2 to infinity. And so you see I broke this integral up because I'm using the sum rule for integrals in such a way that each integral only has 1 bad point to deal with. Right, so I know 1 is a bad point and infinity is a bad point. And so I sort of break up my integral, so I have to deal with one of these at a time. And how I'm going to deal with this one is I'm going to take a limit to approach 1. In this case from the left. Here I take a limit to approach 1 from the right. Here I take a limit to approach infinity from the left, and sort of see how this function behaves. Yes.
I just want to clarify that. So this like bad point is just like a hole in the graph.
Yeah, or something else. It's going to be a point where our function is either undefined or it's infinite.
Oh, okay.
Right, it's where our f of x does not behave at some point. You can't really plug an infinity into a function technically, and as well as it might be undefined at some point. So these are bad points. We can't actually plug them into our function, so we use limits to approach them. And so, how our strategy would work here, I'm just sort of giving you an overview of the process.
So when we take the limit as we approach 1 for both those integrals, would it be the limit from the left? Like from...
This one is from the right, this one is from the left.
That was from the right?
Yeah, because look at this interval, what does it describe? It goes from 0 to 1. So we're actually approaching 1 from the left, because there is no right side.
Mm-hmm.
This one goes from 1 to 2, we'd have to approach from the right because there is no left side.
Okay.
And then this one would go from 2 to infinity, well you're always approaching infinity from the left.
Okay.
Alright, so our strategy then to compute this integral would be something like this. I would take the limit as, say, m approaches 1 from the left of 0 to m of this function. Alright, so I replace the upper limit with a number, a variable, and let that variable approach 1. Plus, I would take a limit as x approaches, as I'll use x, let's say n. Use a different letter because you don't want things to mix up. You don't want to mix things up. And so this would be n approaches 1 from the right of n to 2 of f of x dx plus the limit as, say, p approaches infinity from 2 up to p of f of x dx. And if each limit exists and gives us a finite value, then the integral converges. Otherwise, it diverges. So converges means when I do this process and I take all the limits, they actually give me nice values, which means I could have essentially ignored them. And so, but if that doesn't happen and the function cannot overcome all these bad actors, then it diverges. Right? So that means the integral will either go to infinity or I won't, the limits do not exist, I won't be able to put a meaningful answer on it either way. One thing I want you to note here is that if any one of the limits in the breakdown So you can think, each of these guys are computing a segment of the area under this curve. If one segment goes off to infinity, then even if these two behave, overall the area goes off to infinity. You can't save it, right? So if any one of these guys mess up, the entire thing, the entire game is off, the jig is up, we go home. Where we are. Been talking on top of my head for a while. Let's see. Okay, so I define what improper means. So we got limit. Divergence. We can start on some examples finally. Start with some easier examples to illustrate the point, which leads to a general fact which we're going to use later. So where are we? We're going to use the same integral, but we're going to do several different limits setups so that you can see the difference in approach that these guys will take. So A, we're going to do from 1 to infinity of 1 over x squared. E. We're going to do from 0 to 1 of 1 over x squared. C. We're going to do from 0 to infinity of 1 over x squared. We're going to do from minus infinity to infinity of 1 over x squared. E. We're going to do from 0 to infinity of 1 over 1 plus x squared. F. We're going to show the fact that the integral from 1 up to infinity of 1 over x to the p converges if and only if p is greater than 1. After that, we're going to talk about the comparison theorem so that we can compute improper integrals without computing improper integrals. Okay, but that's sort of where we're going to go. Full disclosure here, like at this point you've covered all the integration techniques, so when I'm doing this I won't necessarily give you a very nice function to work with. I expect you to remember your integration by parts and use whatever techniques are necessary. Also, when it comes to limits, you might also get limits where you have to use sophisticated things like L'Hopital's rules and all that. So you're not allowed to forget what we've done before. They will come up in this situation. I'm just using a very simple integral here because I want to illustrate the point rather than teach you how to integrate because I've already taught you how to integrate. Okay. So this is just when we're doing certain definite integrals where the limits kind of don't agree with the function too much. And this is the situation we can end up with. So let's actually do part A, for example. Okay, so tell me, now this is an improper integral, but why is it improper? Yeah?
Because the value of b is infinite.
It has an infinite limit. Limit on the integral. Okay. So you see something like that, it's immediately known to be an improper integral because it has infinity just glaring at you there. So how do we actually deal with this? Yeah?
You split the infinite.
Why would we need to split it? Are there any other bad points?
Oh, yeah.
Other than that infinity, does 1 over x squared behave on that interval? Right, no. That's the only problem, the infinite limit, right? 1 over x squared is defined for all x except x equals 0, but x equals 0 is not on that interval, so I don't have to worry about it. The infinity is the only problem here. So what I would do is, this guy is going to be equal to the limit, let's say as n approaches infinity, of 1 up to n of 1 over x dx. X squared. Now, as long as that limit exists, this, I would say, this converges. And, yeah.
Sorry, so when you say like the limit on the integral, do you mean like just the bound?
The bound is on the integral. Yeah.
Okay, so as different from like a limit that like.
Yeah, it's not the limit like
Okay.
approaching. It's here I'm saying it has an infinite limit on the integral. Yeah, it means like on the limit here.
Okay, alright.
It's just a coincidence that those things are called the same. Okay, so now what?
Figure out the limit and work a lot to the right and see if it exists, or
Well, now what you do is you first do the integral right? And then you'll get a function of x as a result, and then you take the limit of that function,
So,
right? So we're going to take the limit of that integral, so first we're going to do is find that integral. How would I find that integral? What is that integral? How do you integrate 1 over x squared?
Do improper fractions.
What?
You do improper fractions? Sorry, partial fractions.
just x to the negative two.
Which is actually
and then-
negative 2.
Thing way too complicated. X to the negative 2.
Oh, I always do that.
It's x to the negative 2, so we can just use the power rule.
Negative
Right.
x to the
This is
negative.
one of the things where you really want to start out simple. You never jump to something like partial fractions. No, you first consider, can the power rule work? No, can substitution work? You build up slowly. You don't jump all the way. Let's do a trig sum. You don't go there, right? You try to see as simple as possible. And so, yeah, now you just do the power rule. You add 1 to the power divided by the new power. And fundamental theorem of calculus applies. And so now we'll get an expression. So what this gives us now is the limit as n approaches infinity of, I would plug in the n, it's minus 1 over n minus, plug in the 1. So the limit is just hanging out. I'm really just evaluating this integral as I would normally evaluate an integral. Apply the fundamental theorem of calculus as I normally would. But now I get an expression with n in it. And so now I can take the limit of that expression. And what is going to be the limit of that expression? Yeah?
Why did you get the 1? Like
Negative 1 over 1.
Yeah, it's negative 1 over 1. So if I were to write this out, it's me plugging into the thing. So fundamental theorem of calculus is the top one minus when I plug in the bottom one.
Oh, okay.
And what does that limit approach?
Negative 1? Or just
1.
Just 1, because this guy goes to
Yeah.
0. And so that actually approaches 1. And so we say this guy was 1. It converges to 1 is another way that we could express that. And basically what that means is, paradoxically speaking, if I look at the function, if I look at the right side of this function, starting at 1 and going off to infinity, I can actually measure the area here. And it turns out that the area is 1. Or in other words, the area will approach 1. Like the more I compute the area, the closer and closer I will get to the number 1. So I just consider the area under the curve to be 1. Yes.
So like converges to 1 means that you can find the area?
Yeah.
So what is the other word, divergence?
Means I can find the area. Which means either the area goes off to infinity, like it just keeps getting bigger and bigger and bigger, I'll never get to a number where I can say that's the area, or the function is so crazy that I can't even put a number on it. So either of those is bad. So that's an example. Here, so we've seen an integral. It's clear that it's an improper integral because I have the infinity. What I then look at is the function itself. Does this misbehave anywhere else? So that comes down to you finding the domain of the function and all that. Here it was fine. The only other bad point is x equals 0, but that is not in consideration here because x equals 0 happens over here and we're over here, so it's not a consideration. And so I only have one bad point to contend with, so I take the limit as I approach that point. First do the integral, all the old integral rules apply, all the old integral techniques apply, but try the simplest ones first, do as needed. Apply the fundamental theorem of calculus, you get an expression now, this is going to be a limit. And then you use all your old limit rules to find that limit, right? Let's look at B. Now, of course, that's improper, but I just want you to just tell me why.
Undefined. Undefined at 0.
This is improper since 1 over x squared is undefined at x equals 0. So in this case, x equals 0 is the bad point. So that one was the one that's jumping out at me, but we still have to consider, does this actually misbehave somewhere else? It actually doesn't, so there are no other bad points to worry about here. So that's the only one. But let's look at this one now. Now it turns out that the infinite area going off that way converges, it exists. What about the infinite area going off this way, up the y-axis? Well, let's see. Does that actually work? So what I would do is I would take a limit. So I'm going to take the limit as n approaches 0 from the right, because clearly I'm on this limit here, 0 to 1. So clearly I'm filling in stuff that's to the right of 0, so I'm edging this way, because at 1 I have no problem, so I just inch towards 0, that would be coming from the right. Of n to 1 of 1 over x squared dx. Same things would have happened. So again, I consider it just as a usual limit, so this is just going to be the limit as n approaches 0 from the right of this guy from n up to 1. That's going to be the limit as n approaches 0 from the right of, plug in the 1, plus, plug in the n.
Infinity.
Right, that goes to positive infinity. So this means what you would say is 0 to 1 of 1 over x squared dx diverges. So it turns out that sure, we could handle going an infinite direction in the other way, we couldn't handle division by 0. It was catastrophic here. Yeah.
How come your area can't be a infinity?
What do
Like,
you mean?
how come you couldn't get an infinity as an answer for an integral?
Well, it doesn't really make sense in, I mean, it depends on the context, but for us, it's not something that makes sense.
Okay.
That it takes up an infinite amount of space. What does that mean? How is that applicable?
Okay.
You know, there are other contexts in which that would make sense. For us, it doesn't. We like our areas to be finite around these parts.
How do you know it's
I mean, there are math classes where you'd even consider infinity just like another number on the number line. But here we don't do that. Yeah,
How do you know it's infinity?
because I'm plugging in 0 here. In other words, I'm thinking of the function y equals 1 over x as x is approaching 0. That function looks like this. As I'm approaching 0 from the right, my function is going up. Goes off to positive infinity. Right? If it were the case where I'm approaching 0 from the left, it would go to negative infinity. That would be just as bad. But yeah. Okay. What about 0 to infinity?
It's undefined and infinite.
You already know it's going to be undefined, but let's actually pretend it was a problem that we didn't know what was coming. So this is improper. Oh, no, we're almost out of time. So this is improper, and now it's improper for 2 reasons. One, there's an infinity in the integral limit. And 2, 1 over x squared is undefined at x equals 0. Now how do you actually deal with that?
Break it up.
We have to break it up, because notice that there are 2 bad points here. So what we would do is we would break that up. So if I have 0 to infinity of 1 over x squared dx, I'm going to replace this with 0 to say 1 over x squared dx plus, say 1 to infinity 1 over x squared dx. Now as we've seen, this guy converges. This actually gives us a number. Right, so it contributes a +1 to this thing, but we know also that this diverges. If one of them diverges, the entire thing diverges, because if you take infinity and add 1, you just get infinity again. It still messes up. Right? So overall, the integral diverges because one of the pieces diverge.
Is there really any instance where you get like negative infinity?
Oh yeah, it's possible that way. I think I even did it here.
Oh, gotcha.
So it's definitely possible.
But like, if it's, since we're talking about an integral and the area is supposed to be positive, does it just not make any sense since the integral?
No, the integral, remember, we think of it as the net area under the curve. So there are times when we say, when we see the area negative, we just assume that the curve is just underneath the x-axis.
Okay.
We consider that just as before. So we'll know if we actually care about the positive area, we just negate that part of the integral. We'll stop there, we'll finish up these guys here, and we'll talk about a theorem that allows us to compute integrals using other ones so we don't directly attack them. And we'll look at that tomorrow. Huh?
How do you know
We did this.
Oh, okay.
This we did in part A, and this we did in part B. Right. But if you weren't sure, you would have done that. You would have done what we did in part A and part B. I'll see you guys tomorrow.